highly.
Okay. I noticed that there is a joke in your handout here. Are you intending to refer to the joke in your talk, or would you like me to point it out now?
I don't even remember what it was.
Okay. Well,
I think you might as well point it out now.
Okay. So I will point it out. Right. So Paul has been kind enough to create a glossary for non-programming languages people. Okay, and if you look down, and he's actually been kind enough to include what is either a joke or an example of the kind of bug that his work is designed to avoid. Okay, and that is...
I'm starting to worry this may have been completely unintentional.
Right. Is the most basic way to make names bound instead of free. The code lambda alice ... is like pointing at someone and saying, call that person Jane Doe. And I think it was supposed to be Alice.
You're right.
Okay, so Paul has...
It's totally unintentional.
So Paul has been here. If only we had a system that would help avoid such errors. So Paul has been here for some number of years.
It's pretty high.
Say again?
It's pretty high.
We don't make value judgments about the number of years. Too depressing for everyone. So in any case, this was Paul's defense, and most of you know, but I will repeat the agenda again, okay, which is that Paul will present for 40 or 45 minutes, maybe less, who knows. He will. Sorry, I've had too much coffee. Paul will present for between 30 and 45 minutes. At the end, the audience will have an opportunity to ask questions. When the audience is out of questions, they will be excused, and Paul will be questioned by his committee, which consists of Olin and Amal and Robbie Findler, who is on one or another of the video streams. In private. When we are finished with Paul, we will excuse him, and we will confer, and at the end of that time, we will come out and give Paul our decision. Okay, so that's the rules of the road. Paul?
Thank you. Okay, here's a piece of code. This is a meta function, and it has a cursor on it. It only made matters worse. There we go. This is a piece of code. It's a meta function written in Redx, which is a meta-programming system. And it's supposed to count the number of references to x in any term. So the number of references to x in the term x is 1. The number of references to x in any kind of list, to calculate that, you just sum the number of references to x in all of the elements of the list. Anything else is something special and random, and it doesn't contain any references to x. This code is right, I would claim. But up until recently, if you ran it in Redx, you would get this result, which is perhaps not unexpected. If you count the number of references to A in A lambda B B, it would say there's 1. If you count the number of references to A in A lambda A A, it would tell you that there's 3. But lambda is a binding form. This A here is a totally different, these two A's here are a totally different animal than this A, and it shouldn't be conflating them. Really, because A lambda B B and A lambda A A are alpha equivalent to each other, they really ought to behave the same way. So this principle is something that we can formalize by saying that for a program, alpha equivalent inputs should produce alpha equivalent outputs. This is our binding safety guarantee. It's a nice, simple mathematical thing. It's quite useful. Not a lot of systems provide it. So here are some examples. Up until recently, Redx didn't provide any name support. Lem is another sort of similar system. Also, there are a lot of practical metaprogramming systems in the world, like C++ templates and Lisp macros and template Haskell and MPS and SpoofX, and these things also allow you to have wrong things happen because you defined something using the wrong names. Racket is on this list too, which you might be saying in your head, it's like, didn't I hear that Racket has this nice hygienic metaprogramming system? And it's true that Racket is hygienic. However, hygiene is essentially a stab at the correctness criterion that we gave that doesn't really actually make it all the way. The correctness criterion for Redx, for hygiene and Racket, isn't really all that well defined. It's just like it happens to prevent name clashes most of the time. So we want something that always works reliably, and it would be nice to follow this rule. There's some systems that sort of take us part of the way. They allow you to specify the binding structures that you intend to be present in your language. And then they will write a capture avoiding substitution for you. And then you can use that. And as we're going to see, this saves a lot of work. But what it doesn't do is save you worry, because it doesn't keep you from accidentally writing some code that does behave differently based on what names you happen to have chosen. Like, for example, the code in the first slide. Substitutions in our reference to X counter. So making substitution capture avoiding necessarily doesn't help. So we really want a system that just works automatically, regardless of what you do. There are a few systems that do have this property. MetaML and PureFreshML allow you to define binding specifications for your language, and alpha equivalent inputs to programs written in those things produce alpha equivalent outputs. It's great, except that these systems only support really simple binding forms. So the lambda example, that would have worked because you can express lambda. But they basically don't give you the power to express more complicated binding constructs. And since metaprogramming is something that's really useful over real-world languages, we have to deal with the fact that real-world languages have really complex binding constructs. On the left-hand side in Racket, we're using the let star binding construct. We're doing some sort of, it looks like a progressive refinement. We're taking A, it's a zeroth approximation. We're refining B and C in terms of it. Each of these arms of the let has access to all of the names defined before. Furthermore, the body of the let also has access to all of the names. In this SML example, we have something that's called local. It's apparently being used by a partisan in the tau pi debate who doesn't remember what tau is, but wants to make sure that the clients only have access to tau. So you are allowed to have some internal definitions underneath the local here, use them to define the definitions that are actually useful and available in the program at large, and then use them in the program at large. So none of these things are expressible in systems like PureFreshML, and that limits its applicability to metaprogramming. So today, I'm happy to report that if you ran the code, if you wrote your binding specifications up and ran the code that I described, you would now get this result in Redx. You're going to get the same result regardless of what names you chose in the lambda. Furthermore, it also works for complex binding structures. This code, I think, is pronounced let. So that we can usefully manipulate syntax in an automatically binding safe way. Even this kind of syntax that has complex binding patterns. In order to do this, there are sort of two prongs of this. The first thing is that we built a core calculus called Romeo, which supports complex binding structure, and we proved that it obeys the safety guarantee we described. However, core calculi are nice in theory, but completely unusable in practice. So we took an existing, large, useful, practical system, PLT-REDX, which real people use. They're programming languages people, but those count as real people. And it's based on Romeo, but it's actually useful. And I can tell that it's useful because I've gotten bug reports against it. But first, let's talk about Romeo. Romeo, as you may have guessed, its name is based on the work of the prominent nominal logician William Shakespeare, who said, "What's in a name? A rose by any other name would be something like that." I just realized that I forgot to disconnect from the internet. It's a good thing Vincent's not still around. So Romeo supports flexible binding structures. These are things that you define in Romeo's type system. But Romeo's type system is kind of ugly, so I'm going to show you some boxes instead. First, let's start with the simple stuff, the lambda calculus. It's only got one binding construct, lambda. A lambda has two children, a binder and expression, and the binder is in scope for the entirety of the right-hand side of the lambda. And the other parts of the lambda function application and variable reference are just basic and simple. So, you can plug these things together, make a nice abstract syntax tree. If you want to talk about lambda x, y, it's going to look something like this. And this demonstrates one of the things that almost all binding systems have in common, which is that if you bind something in a particular term, it's automatically going to be bound in all subterms. This is just a convention. There's no mathematical read this way, but it seems to be what programmers always want. So this means that we don't draw down arrows. We just say, like, this x is being bound in here, and therefore in all subterms of that term. But let's do something a little more complicated. In particular, what if we had a binding? What if we were able to import? I'm calling these sort of horizontal arrows import from something that wasn't just a binder. Well, if you want to import from a term, we need to specify what's going to happen. So here I've written something. I've written a simple let, and I've pulled out this little clause here. Let's call it declaration as a separate term. And it says that it exports its first child. And that means that when you import that term, when you import the term that represents that decal, it'll present as an X. So this, has a similar binding structure to what you've already seen. This, in and of itself, isn't very exciting. You could obviously flatten this into this and represent the same thing without this complicated up arrow. But the nice thing is that it's not a big step to doing multi-armed let. So this is about the extent of what other systems have proposed for being able to manipulate in a binding safe way. But I would claim that they do it in a somewhat hacky way. So what we do is we say, each clause of the let consists of a binder, some sort of expression, and the rest of the clauses. So standard linked list representation. This allows us to say, well, each of them exports the binder, the rest of the clauses, and this whole thing winds up importing x and y into the right-hand side of the let, which I've elided. Now, of course, I'm really excited about let star, so let's change this to let star. In let star, this x is going to be supposed to be bound instead of free. So let's add a star, and also add an extra import here, which says that this x is bound in all of the successive terms, which means that this x is now bound instead of free, which is what we wanted. This is something that's unique to just in Romeo, and this, especially the fact that binders are able to flow in multiple directions at once and still be treated safely. So let's talk about safety. So safety is enforced by Romeo's runtime. There's sort of two prongs to this. The first is that Romeo uses freshening in order to prevent name collisions. And the second is that Romeo gives an error instead of allowing you to leave names unbound. And if you don't like errors, there's a deduction system which allows you to rule them out. So first, let's imagine that we're executing some Romeo code. The current things in our execution environment are abs, which is some sort of lambda, and ex1, which is just some sort of expression that's got a free a in it. And naturally, we've got ourselves set up for a collision because we want things to go as bad as possible in this example. So let's do sort of one of the obvious next steps that we could do in this program and unpack abs. So we're going to destructure it and pull out the binder and the expression on the right-hand side and make them their own separate variables, like so. And now we've got a problem because this A, Adam, and the A in expr are supposed to be related to each other because they were related to each other in the lambda. This A is something that's supposed to be totally different. At this point, we're doomed because if we try to build stuff using these things, we can't tell the A's apart. So we needed to have done something different when we unpacked them. And what that is Romeo is going to pick a new name, let's say B, because B isn't used currently, and it's going to change this bound name to B right before it unpacks it, like so. Now you can construct things using these dilly-dilly, and you're not going to get any name collisions. This system ensures that if two names are equal, it's because they were both pulled out of the same construct at the same time. So that's how we prevent name collisions, but there's another part. Let's imagine that we're writing some sort of function or program that takes some sort of lambda and spits out the binder of that lambda. So it takes lambda AA and returns A, lambda BB and returns B. If we do this naively, we're going to just return A and B. But these two things were alpha equivalent to each other, and A and B are definitely not because they're different and there's no binding structure at all. So this is wrong. But wait, we're doing variable freshening, so you won't see this behavior. It's great. Instead, you'll get X and Y, which is different but still not helpful. Since freshening is non-deterministic, we can't recover this guarantee of determinism. So in order to get that, one thing we could do is we could say, let's just say that the first binder is always BDR0 and the second binder is BDR1 and so on, and canonicalize, which solves the problem. But we've now turned this function into something that always returns the same value. Functions like this will tend to become kind of useless most of the time. So really the solution is don't do that. The solution is that we're going to detect cases where names are escaping the context in which they make sense and turn that into an error, and that preserves our guarantee. If you don't like runtime errors, there's an out for you. It's possible to use Romeo's static deduction system to prove that these things won't happen. And here I want to plug Fabian's work when he was a master's student here. In taking the really complex deduction system that makes it possible to make these things safe and turning it into a user-friendly system that gave good error messages, which is always really tricky. And I'm a big believer in the importance of good error messages. So let's take Romeo up for a spin. I'm going to do an example of desugaring, and I also want to use this to highlight the way that safety guarantees can make programming easier. So suppose that we want to desugar away let stars. I've got a little reminder of structure of let star. I didn't want to write down the complete binding specifications because I think, as I said, Romeo binding specifications are on the ugly side, and there's already a lot of text on the screen. But Romeo's type system is going to know that this let star has the appropriate binding structure. So let's just use it. Let's say that we've got a bit of syntax and it's a let star that has no arms. In that case, it's just equivalent to its body. So we recur and desugar its body, which is pretty simple. Finally, it's like, okay, well, what if we get a let star that isn't trivial? It says X is equal to val, and it's also got some decals, some remaining decals in the body. We desugar the smaller let star that we can build from that. And finally, we get around to actually doing something. We need X to be bound in both decals and body. So let's just wrap the whole thing in a lambda that binds X. And then in order to get the correct semantics, we will want to do the left-left lambda thing and apply that lambda to val. So this is basically the way that you would write a let star desugarer in any sort of macro language. But the exciting thing about Romeo is what we discovered happens if you want to write let instead of let star. So let's remove all of the stars from this code, switching us to talking about lets instead of let stars with this different binding structure. And then actually not change the code at all. Now this seems a little bit suspicious because we've got this decals, which no longer should have X bound in it, underneath a lambda X. So X is going to be bound in it, right? Well, it's going to be safe, and I think that it's easier to explain in terms of the safety guarantee rather than in terms of freshening, which is kind of exciting to me. I like thinking about safety guarantees rather than about how they're implemented. So what I would say to myself when I'm writing this code is, so I'm worried about this X being bound in this decals, which means I'm worried about writing a let which has some X in it, and then further down I'm using an X which shouldn't be bound but gets bound. Well, that problem wouldn't happen if I had chosen to write Y instead of X, and those two things are alpha equivalent according to our binding specifications. So this means that your Romeo program cannot tell the difference between the good case. It can't tell that you use the same name. So this means that somehow freshening causes this X not to incorrectly bind in decals. And you can sit down and work out how freshening does it, but I think it's easier to reason in terms of the safety guarantee. Let's talk about readx. So Romeo is not a practical system, but PLT regex is something that people actually use. And sometimes using regex is hard. So this is the way that you would do capture, avoiding, substitution in regex. You don't need to actually read this code. Just appreciate that it's kind of long. This is actually from a library that regex uses that works if the only binding form in your language is the lambda calculus, is lambda. So presumably you're working in the lambda calculus. But if you want a more complex binding form, you're going to need to rewrite this and also write additional clauses to deal with freshening in the case where in the case of your new binding form, which is a pain. Now the situation is much better. If you want to do capture, avoiding, substitution in regex, now you can write this, which is the most naive possible way of writing a substitution. And we know that it's capture avoiding because name collisions can't happen anymore. And this supports all binding constructs. You just need to make sure to define them when you're defining the language. How do we do it? Well, we have a syntax for defining the binding specifications that are part of your language. So everything outside of this red box is the way that you used to write regex in the old days. The red box is the new stuff. Now you say, it's like, okay, I've got the lambda calculus with X, and it's got E, which can be X or a function application or a lambda. And if you ever see a lambda, then you know that in the expression, the names x1 ... are in scope. So this is all you need to do to get your program to be binding safe. Oh, sure. So what Shadow is expressing is that if there are some identical names in this lambda, the names on, I think it's the left, but I always get it confused, take precedence. The sort of traditional thing to do is to say that the lambda is a rib, which is to say that it's an error to use two names at the same time. However, we discovered that there never was a good place to actually enforce this error. since it's something that needs to be reported to the user of the object language rather than the Redux user, it's not really Redux's job to spit out errors that would then need to be translated for the user's sake. So we think that it doesn't really save anybody any effort to do the rib enforcement for them. So Redux, when you say I've got multiple names, you have to specify which order they shadow. You're not allowed to say, oh, it's just an error to have two of them be the same. I don't know if you were asking about shadow versus rib specifically. Okay, so we weakened the safety guarantee in Redux, and I want to tell you why. So as I said before, Romeo's safety guarantee is kind of has two prongs, but these two prongs are kind of lopsided. So the avoiding name collision part is something that happens automatically. It's just like Romeo does the freshening for you, and then names just don't collide. On the other hand, fresh name escape is different. One thing is that different in two ways. One of them is that, as we'll see, it doesn't provide as important part of the safety guarantee. The other thing is that it's kind of a user hostile feature. You either have to have this really complicated static analysis system, which requires an entire master's thesis worth of work just to make the error messages be user friendly. And if you don't use that, you still have runtime error messages. And I find it kind of hard to write these error messages, which is a little bit suspicious. It's like, what do you mean that it's wrong that my name is escaping this context? Since it's kind of hard to explain, and also because I was sort of judgmentally calling some functions useless, and theoreticians like to say this is useless. And practical programmers sit down and it's like, well, that's what I want in this case. So maybe we should investigate what happens if we just let people allow fresh names to escape. So let's take part of safety of Romeo's enforcement system, and we wind up getting a safety guarantee that's actually pretty similar. Alpha equivalent inputs are still going to produce similar outputs. They're just not quite as similar. What you can have is you can have the same input produce lambda xy, xy AAB, and lambda zw, zw ccd. The x to z and y to w things are what we would have expected. But now these free names are sort of being treated as though they were bound. Crucially, you can't get zwccc or cdd. The same structure has to be present in both of them. And what these names, these exposed non-deterministic free names are, is they're really names that the programmer forgot to bind. So the way that it usually works out is this. Imagine that you're writing some sort of Redux model that has mylab. And you say, okay, in E, I've got X, X is imported in E. But you botch the implementation. Let's just say that you forget to you drop X and V on the floor, and you just expand mylab away to just its body. So this is the incorrect desugaring. And you'll notice that we've created an error because this X is now free, so this code is not executable. Romeo could have statically told you that this expansion was bad because it was going to produce a free variable. With a weakened safety guarantee, we can't detect this. But I would claim that this is a fairly easy bug to test for. Free variables aren't the sort of thing that cause things to go subtly wrong. In particular, my first worry when I saw this problem was, what if I wrap this whole thing in something that binds X differently? That's supposed to do some shadowing. So if you try to bind X to 6 and then try to bind it to 5, here should be 5. Your error has made it so that it's unbound. But crucially, during expansion, freshening is going to make sure that this binding relationship is respected, even though the binder isn't there. So the only thing that can happen is, the only things that can happen to you in this weakened safety guarantee that couldn't happen previously is that you can wind up with unbound names. And since that's an easy thing to detect, and since the whole apparatus around preventing it is not very user-friendly, it seems more sensible to just have the good part that's easy to use. So let's talk a little bit about how we adapted our ideas to Redx. So Romeo is a statically typed system. Redx emphatically is not. It's so much so that when you construct a value in Redx, the value doesn't even know what language it's in, which means that you have these values floating around, which are sort of essentially just literal text. They don't know what their binding structure is. The solution is always pattern matching in Redx. And what we do is we take advantage of the fact that when you actually go to break a term apart in Redx, Redx needs to know what language you're operating in. So if you've got some sort of binding form declaration, what Redx does is it says, okay, if a value matches this particular pattern at the time that it's being destructured, it is a binding form by definition, and therefore will be freshened. This is something that happens, it just sort of happens just in time. And it sort of matches with Redx's general philosophy that things acquire their identity by being matched to patterns. So I've claimed that Redx is practical, and I've claimed that our additions to Redx is practical. The way that we evaluated this claim is we took existing Redx models. Redx comes with a large library of examples, and we added binding specifications to them and saw how they changed. I'm going to put a lot of, let's say, lines of code on them. And while, you know, in general, lines of code, fewer is better. I don't want to endorse like lines of code as the be-all and end-all of testing of like code quality. However, I think that in some cases the differences are sufficiently dramatic that it suggests that it's significantly easier to create new models using binding specifications than if you can't. So first, we took a really basic example about church numerals. This example was sort of perfect for our system because it has both, it's basically the lambda calculus plus let. So half of the forms in the language are binding forms, which means that a big chunk of the definition of this model was a big capture avoiding substitution. And with our binding forms, because capture avoiding substitution is much simpler, we're able to cut that out and make this program a lot shorter. Letrec.rkt is kind of exciting, partially because it tells a story. So letrec is this complex binding form that has particularly interesting semantics, especially when it interacts with continuations. And so it's important to hammer down what is supposed to happen, build the semantics for this. Redx is a great tool for that. But you can see, based on the top of this file, that whoever was writing this wanted to get down to actually writing the semantics of letrec, and then said, it's like, shoot, I have to write a big capture avoiding substitution. I'll just use a library for that, the subs.rkt library, the one that I showed you earlier, the one that only supports lambda. So they knew that the capture avoiding substitution that they had just wasn't aware of the binding structure of let and letrec. And they just said, they just put this thing here as a warning to future users not to try to be careful about name collisions with those things. When we added binding specifications, we were able to take out the reliance on that library and fix that bug without really going into any effort. There's some more exciting things in this file. One of them is an example of how binding forms are not necessarily just syntax. So the binding forms in this language are, you know, lambda, letrec. Then there's this weird store thing, left store. This is really a machine configuration, but machine configurations have variables in them. They've got chunks of syntax in them, and those chunks of syntax have references to those variables. So we can model that in our system. And this allows you to, for example, have tests that acknowledge the fact that the machine state in which A is bound to 5 and you're going to return A is exactly the same as the machine state in which B is bound to 5 and you're about to return B. Letrec also has another example, an example of why just having capture avoiding substitution available to you isn't sufficient for safety. So here you can see a little bit of code, and if you're converting something to use binding specifications, your eye immediately leaps to this variable not in thing. That's a way of, in regex, saying, I want to create something that's based on x1, but I'm worried that x1 collides with something in the store. So let's freshen that up. But since we've got our language binding specified, instead we might want to look at where x1 comes from. It comes from this let. And since that let could possibly have had a different name, one that doesn't collide with the store, this means that by our safety principle, it'll behave exactly as if it did have a name that didn't collide with the store. So we don't need to freshen. We can cut this out. And we can also cut out all this sort of support structure to deal with the fact that we've just changed a name, which means that we get to rewrite the rule like this. And this is something that kind of excites me, because this means that if you're programming applications, you kind of have to worry less. You don't have to say, it's like, do I need to worry about whether this name collides with this? You just unpack, repack things as much as you want, and you never need to gensum up a fresh name. LetRec didn't get a lot shorter in this process, because really all we did was we cut out those couple of lines and removed the use of a library that wasn't appropriate for it. But we did increase its correctness significantly, and I think that that's also worthwhile. Because all of the binding forms that I've shown you so far start with L, I wanted to show you that this works for other binding forms. So we also took a look at the pi calculus, which has totally new binding forms. And we were able to shorten that file significantly also, because of course they had to write their own capture avoiding substitution to deal with these different binding forms. Finally, we wanted to look at something big. So R6RS, the big scheme standard, its semantics are formalized in regex. So it's this big, huge regex model that conveniently has a lot of binding forms in it. So unlike the other examples here, adding binding forms to this was a significant amount of work. Part of this is because the way that this model was designed kind of bumps up against the way that we detect binding forms by pattern matching. Essentially, there were certain patterns that either were or weren't binding forms depending on where they were used. And also the tests for this like to poke into internal state and take apart names. So we had to adjust the tests a little bit also. But as people who saw my practice talk can attest, this doesn't take too much work, because I hadn't actually done this at the time of the practice talk. So I would say that even really complex regex models can benefit from binding specifications without a huge amount of work. So we shortened it by about 8%, which is 63 lines. The original capture avoiding substitution was about 100 lines. So you can see that we had to add a little bit of extra structure. But in the process, we made this file a lot simpler. And we also wind up putting the binding information not in some capture avoiding substitution, but in the definition of the language, which is where I would argue is where it belongs. So I'd like to thank you all for listening to this, and thank my committee, and Katie, who's been really helpful with making this make sense and also handling the really complex AV setup. And I would like to ask for your questions. Yes. We don't have any direct support for that. My suspicion is that it wouldn't be a difficult feature to add. And we should talk about this, because I think it might be something that you get automatically, because if you have, no, that's not true. But I do stand by that it wouldn't be a difficult feature to add. So you have one sort per type. So this means that the name lookup process has to interact with the type checker. Sounds exciting. That I'm not going to claim is easy. but I think it's something that I think that if you really want this, this is probably the direction to start. But it probably is a lot of work. So stronger safety guarantees than our guarantee than like the stated alpha equivalence preservation.
Preserve the information you had that you can implement the function you want to implement, but you have a stronger guarantee that when you have the regex version of the.
I don't think that we provide support for that. It seems that it's like strengthening the safety guarantee beyond looking at just alpha equivalence means that we're going to need some additional information to enforce that. So I think that would be quite complex to add.
So you made regex writing vector loading easier. Why don't you write it for them automatically? Is there a fundamental reason, or you just didn't do it?
We actually do. So actually the substitution meta function that I described, what is it? This one here. Isn't actually what you use. What you do is you just assume that this is defined and is called substitute. Yeah. And because we do that, we're able to do a little bit of optimization. But R6RS wasn't able to take advantage of that because R6RS wants an idiosyncratic substitution that it doesn't substitute under quotes. So we weren't able to use the built-in meta function. So R6RS's substitution does look a great deal like this. But you're right, this should be provided, and is. Not in the current system. Well, no, I think that it's like that is what quote is. Quote does sort of suppress the. In some sense, quote is actually the exception to the place where I said all the arrows always point down. It's something that prevents the arrows from. Yeah, we can't express quote directly. It's another thing where I suspect it'd be fairly easy to add. And come to think of it, since it's an exception to my claim that everybody always wants the implicit arrows downwards, maybe it's a feature that's actually interesting. I mean, definitely interesting.
So you use arrows up. There is some information we need to combine. So yeah, like right here, you have two arrows up.
Oh yes, there.
There's information. There's an ambiguity here.
Which order do they? Which one shadows which? So what you actually get in Romeo is you get the ability to say, I would like these two things. I would like these two things to shadow in this order, or I would like to make a rib out of these two things. And you can and if you have a bunch of things, you can nest these things inside each other. It's like, I would like a shadow of these two ribs or something. You can't write arbitrary name combining functions. It's conceivable. Arbitrary name combining functions sounds a little scary, but I don't actually see any obstacle to dropping it in. But it's like that's a sort of scary feature to play around with, partially because these binding specifications really should serve as documentation. It's like they should be part of the documentation of your syntactic forms, telling the users what to expect. And just saying it's like the binding structure of this is this function may not be the best documentation. It's true. I'm making a lot of value judgments on what kinds of binding are most interesting for the purposes of this stab at making it flexible. Rib. Oh. Is what happens when you say, I don't actually want these to shadow in any direction. I just want to say it's an error for these two sources of names that contain a duplicate. Oh, yes.
So earlier when you were talking about in Redux, it's okay for freshman things to escape because they don't get captured by anything else. They just wind up as undone globally. It seems like you could think of that as kind of similar to the situation where you might have an invariant that needs to not hold for some section of code, but should eventually hold again. And you just don't have enough information to say what the scope of that kind of relaxation of the invariant is.
Yes, that is sort of like the fundamental problem that Romeo and actually Pure Fresh ML bump up against, is that the safety, it's like the restriction is really just that fresh name, that non-deterministically generated names, either non-deterministic from the binding forms of the input or non-deterministically generated, shouldn't escape the program as a whole. That's the most that's the most generous view of that safety of that requirement. But it's totally non-compositional because you're just saying don't do this in the entire program. So the rule in Pure Fresh ML that we borrowed for Romeo is just you can't have things escape the right-hand side of the match structure which broke them apart. And you can kind of see, it's like, that's a really annoying thing to explain. It's just like, really, that's the thing that balances compositionality, and it also matches the way that programmers tend to write stuff. But it is kind of ugly, which is, yeah.
Can you think of a way of describing the section of which the invariant is allowed to be relaxed? Or secondly, can you think of this kind of, for example, can you tag a fresh name with the thing that generated it, so that if it does escape the program as a whole, you can say, this is where it went wrong. This is, I mean, it seems kind of like a contract-like situation. If you unbind, if you destructure something and generate a fresh name, you kind of have an obligation
to eventually
find a good home for it.
Yeah, yeah.
To bind it again.
That actually may be a better approach than attempting to do like the Romeo Pure Fresh ML thing, where you just say, I'm enforcing this rule globally, or maybe per function, whatever. And then you say, it's like, okay, here's the name that you broke apart, but never actually got around to closing up again. I think that might be more user-friendly. I think that the additional safety provided by this work may still not justify the extra effort in writing the error messages, trying to explain this to the users in documentation, the effort that the users have to make to understand the errors. But I think that's a better way to go about it. Sure. So the really most basic example that I like is imagine that you have some program that you've implemented that just consists of a single macro invocation, which is something you can totally do because we've got really powerful macros in Racket. In a case like that, the hygiene algorithm actually has no effect on your program at all. The hygiene algorithm essentially inserts boundaries between each macro invocation. And that means that as the macros get larger and larger, it does less and less for you, to the point where if you have the entire program in one macro, clearly there's some sort of structure in the program, but it doesn't have any way of getting in between and actually enforcing that anything not collide with anything else. In general, it's like the more complex you make a macro, the more likely you are to run into trouble. I think that the classic example, imagine that you wanted to write a macro that some sort of like delay let. So you bind X to some expression, but you don't want it to be evaluated just yet. All of your references to X you want to have the macro take all of your references to X and replace them with references to like force X in order to get the delay semantics right. I like this example because there's something a Haskell once asked of me as a representative of the whole world of scheme-like languages. If you tried to write this in Racket or in a similarly big hygiene-like language, you would discover that you're going to get the wrong behavior because you're taking this unexpanded code and just like searching it for all of the occurrences of X. And because you don't know what binding structure something has until it's expanded, you can't tell whether a particular occurrence of X is actually a reference, or it's like the bound X and my lambda X. So you'll just replace all of them willy-nilly. I think that a lot of cases where you use local expand are a symptom of this. Right. So as long as it's like essentially in Romeo, you know the binding structure early, so it's possible to actually enforce it. Whereas in scheme-like macro systems, you only know the binding structure when you've actually fully expanded something. Good question. So we do, because in our implementation we were focused on getting it right rather than optimizing it, and we believe that a similar optimization to the one that solves the problem in the DIBVIG algorithm is applicable. In fact, one of our next projects, if we have time for it, is going to be to take advantage of the new sets of scopes model of hygiene in Racket to essentially not have to do all of that renaming. So we can actually build Romeo's safety guarantees off of the syntax objects in Racket, we hypothesize. So that would be able to solve the problem of having to traverse the entire term every time you break it apart. Yes?
So suppose I'm writing something that wants to treat variables as variables, and also wants to treat them like, say, I'm writing the collecting non-standard semantics in preparation for doing some sort of analysis, and I want to make a record of all the values or that a variable is bound to.
Okay.
Right. So I for the purpose of evaluation, I want the normal notion of binding, but for the purpose of collecting this information, I want to treat them just as labels. Can I do
are you asking, can you do this in theory in Romeo, or can you do this in practice in Redx?
how about in practice?
I think that you actually can. So in Redx, the safety guarantee is provided that you only do destructuring using Redx match. But Redx terms are just S expressions. You can look at everything inside of them as much as you want just by using car and coulter. So if you go this unsafe route, you could go and find the sort of like nominal name of a particular value in order to hygiene and break the safety guarantee and say these are and say it's like these are all of the things that are called X, regardless of whether they're the same X. So that wouldn't be too hard currently. The representation change that I'm talking about will have the salutary effect of making it a little bit harder to do that, of making it so that it's less easy to accidentally break apart terms, because terms are going to be opaque and only accessible in the ways that we let you. But there's still nothing preventing us from giving you that escape hatch. Because I think that escape hatches are good.
Would it be possible to define two languages with the two different binding structures and use the same term in both languages and get what Ryan is asking for?
Oh, that's totally true. Yes, you can literally translate terms in between languages without any freshening. So you can just have two different languages with different binding structure and also do that.
Any more questions? If not, thank you for coming.
Yeah, thank you. Bye. Okay, I should probably